Einstein's famous twin paradox is not a paradox, but actually completely logical. As a physicist, I want to give you an intuitive understanding of this application of Einstein's theory of relativity, because I often see the twin paradox told with the wrong focus. It gets called a paradox for the wrong reason. And all this, even though it's way simpler than you think, if you understand the basics of relativity. So, I'm gonna show you the building blocks of Einstein's famous theory, and then we'll understand how the twin paradox actually works. The twin paradox is often used to point out that Einstein's relativity is weird. And it is indeed weird, as it is counterintuitive to us. But it has a fully consistent internal logic. The foundation of this logic consists of two main building blocks, and a link between them. First, the principle of relativity. Physics is always physics. Or, more precisely, the laws of physics are always the same for everyone who moves at a constant speed into one direction. Or, even more precisely, this, but yeah. Basically, if you keep a steady speed, physics is always the same for you. You can use physics to make observations and then predict what's going to happen based on these observations. So, you look at the current situation, make measurements and get some numbers. Then, you plug these numbers into the laws of physics, make some calculations, and you get a prediction for the future. Great, sounds like fun. Anyway, this brings us to the second key building block of relativity. That's the weird part of relativity a lot of people are scared of. We may experience reality different. So we might get different numbers if we measure the same things, like distances or times. When you get over not being the universe center, it's not that weird anymore. But we must accept that no perspective is better than the other. No point of view is wrong or right. This means there's no such thing as absolute truth when it comes to measuring distances or times. It goes even further. Distance over time is speed. So there's no absolute truth about how fast something moves. You might see something move slower than me. One exception is the speed of light. See this video for more. If there's no absolute truth about how fast something is moving, there's no such thing as standing still. Sitting in a plane, you pull the blinds down and hide under your hoodie because you like the dark. You doze off, and when you wake up, you can't tell whether the plane is still stationary on the ground or flying at a constant speed. You don't feel any movement. If I see you flying past me, it looks like you're moving relative to me. But if you summon all your energy and pull up the blinds, you see me moving relative to you. One can't tell if something is moving or not, but only if something is moving with respect to something else. In physics terms, we say velocity is not absolute, but relative. Velocity is not only speed, but it's speed with a direction. You have a constant velocity if you're moving at a constant speed into one direction. So you change your velocity if you slow down, speed up, but also if you turn. Changing velocity is what physicists call acceleration. Most people miss that turning is a type of acceleration, yet it's crucial, as we will see later on. So, I know you have a velocity relative to me, but I can't say I'm still and you are moving, and neither can you. No perspective is better than the other. None of us is right or wrong. So, distance, time, and even velocity are relative, not absolute, which means their values depend on perspective. But if time, distance, and speed are different for us, how can we be sure we follow the same laws of physics? We recall the principle of relativity. The laws of physics are always the same for everyone who moves at a constant speed into one direction, which we can now put like this. The laws of physics are always the same for everyone who moves at a constant velocity. So, how do these building blocks fit together? This brings us to the link. Not this one, the other one. We can understand each other's perspective. I can calculate what you measure and you can calculate my numbers. For that, we only need to know our relative velocity and the speed of light. So we need to know how we are moving relative to each other. If I measure your velocity from my perspective, I get our relative velocity. With this relative velocity, I can calculate what distances, times, and velocities you measure. Our relative velocity links our experience, and we can understand how the laws of physics apply to each of us. By the way, it would be awesome if you link your watching experience to this channel. So please subscribe and like, if you'd like to. So, I can make an observation and then use the laws of physics to predict what's going to happen based on this observation. Afterwards, I can take my prediction and calculate your prediction from that. I get the same number you would get by observing from your point of view and applying the same laws of physics. So we can turn one prediction into the other. We can swap our experiences. The laws of physics remain the same, and no perspective is better than the other. If you fly past me and I know the speed of the airplane, I can calculate how much time passed for you. This brings us to time dilation. I give you an intuitive understanding of time dilation in this video. The outcome is, the faster something moves, the slower its clock runs. So, if you're flying past me in your fast-moving airplane, you experience less time than I do. Great, I guess, so less time has passed for you, and when we meet, you're younger than me. I could be annoyed by that, but we remember, I can't say I'm still and you are moving, and neither can you. No perspective is better than the other. From my perspective, your plane flies by, but from your perspective, the Earth passes by. From your perspective, I am moving. So if we turn this around, my time should pass slower. So you're younger and I'm younger as well? Looks like we've stumbled into the twin paradox. Take two twins. One flies into space and comes back to see that they are younger than the twin they left behind. That's the twin paradox. Except that this is not the actual paradox. It's not paradoxic that the twins experience different times, since we learned that time is relative. The twin in space moved faster. The faster something moves, the slower its clock runs. So, they stayed younger. We get to the actual paradoxical part of Einstein's thought experiment if we switch perspectives. The twin in space could argue that they did not move. They just entered a spaceship and then the Earth moved away from that spaceship and came back. Then the twin on Earth should be younger. Don't worry, I got you. The twin paradox is not a real paradox. From my perspective, you are moving. Your time passes slower. But if you want to annoy me with that, you have to meet me first. And that's the crucial bit. You have to turn around with your plane to land on Earth. We remember, velocity is not only speed, but it's speed with a direction. And it's changed by slowing down, speeding up, or changing directions. So, you change your velocity by turning around. You are accelerating. This means your velocity is not constant anymore. But the principle of relativity says the laws of physics are always the same for everyone who moves at a constant velocity. So, if you're not moving at a constant velocity, we cannot swap our experiences anymore. You are accelerating, and you feel it. Acceleration is not relative, it's absolute. It can be measured and felt. You feel the takeoff and landing of the plane. You notice every turn the pilot makes. You can't feel if the plane moves at a constant speed, but you do feel the acceleration when your plane turns. Standing on Earth, waiting for you to come back, I don't feel any acceleration. So our situations are not exchangeable. Your motion is physically different from mine. That's why the twin paradox is not a real paradox. Acceleration made your time pass slower. The twin in space had to change its direction to turn around, and they felt this turning around. The twin on Earth did not feel any turning, so the twin on Earth did not accelerate. Physically different motions. Not a paradox, because the laws of physics are only always the same for everyone if they move at a constant velocity. Moving at a constant velocity, you always have to experience the longest possible time. If you experience less time than someone else, you were accelerating. Or put differently, there was some force acting on you. To learn about the link between forces in motion, or why space-time curves in general relativity, watch this video. Thanks for watching. Drop your questions in the comments below and subscribe to find out how it actually works.